Okay. So today I want to introduce a concept that I guess everybody's familiar with, should be familiar with from kids in grade 6, I think, this thing. Very advanced public school. And this is the Euler character of a manifold. Now, what you would have learned about the Euler character, you would have learned about the Euler character of two-dimensional surfaces, triangulations of two-dimensional surfaces, although your teacher probably didn't call it triangulations of two-dimensional surfaces, given we're still stuck on the difference between disks and circles. But that's what it is. Now, if like me, you were bothered for the first time you learned about this by the fact that you go number of vertices minus the number of edges plus the number of faces. It seems like an empirical fact, right? You take some triangulation and some tetrahedron, you count these numbers and they all kind of come out saying or certain set of objects, and then they tell you, well, it's a topological invariant, and all objects in the same topological class of this object would have the same number. And it seems like that. Today, what I want to do is show you that this V minus E plus F is really a truncation of a much larger sum. Firstly. Secondly, that sum is the sum over simplices. Thirdly, that sum is not an obvious topological invariant. However, because that sum, number of vertices minus the number of edges plus the number of faces minus the number of 0, 1, 2, 3 simplices, etc., is actually equal to a topological invariant. Okay, and by that equality is how we know that it's a topological invariant. Okay, so there's a lot of things that you could do with these topological invariants. There's a lot of different topological invariants that you could define. Remember, this is an elementary introduction to differential topology. The point I want to make that we'll come to in a little bit, maybe not in this lecture, but probably a Friday lecture, is that these kinds of ideas are really deep and they relate things that you wouldn't think would be related, right? So the story that we try to build here is that topology is something that encodes the global properties of your manifold. Right? They involve integrals typically. And integrals means count over the entire manifold. You really need to know what's going on with the entire manifold in order to do the integral. However, when we relate these topological quantities to quantities that involve analysis, and we will see just now that there's this duality called Poincare duality that allows you to relate analytic quantities involving the exterior derivative operator to quantities involving integrals. Right? On the left-hand side, things that involve integrals to topological quantities, they're global quantities. On the right-hand side are things that involve derivatives. Derivatives involve comparing things at nearby points. They only really involve local information about your space. Okay. So the fact that we can relate local properties of spaces to global properties of spaces through differential topology is a really deep statement. There's a lot of really beautiful mathematics encoded there. So what I want to do is first, I want to introduce the Euler character today, and I want to show you that the definition that I'm going to give you is the same as the definition that we encountered in the past. And in order to do that, we need to introduce the idea of exact sequences. And the thing about exact sequences, short or long exact sequences, is that they tell you how to work with alternating sums, like the V minus E plus F minus blah, blah, blah. That's an alternating sum. This kind of telescoping alternating sum is naturally encoded in exact sequences. Okay, so we're going to introduce a particular exact sequence that we're going to be working with. This is obviously the exact sequence of the space of p forms, p chains. And then I'll prove that these two equalities of that these two definitions of the Euler character are the same. And then I will provide the link between homology and cohomology that we've been teaching around for the last couple of lectures. And I'll show you how the Humboldt integral is the thing that provides this. So to start off with, I want to introduce the Euler character. Again, this is not the definition that you would have been accustomed to read. So I'll show you that the two are the same. The Euler character manifold is defined as follows. I of M is defined to be the alternating sum. This is the dimension E manifold. This is the alternating sum from P to naught due to D minus 1 to the P times the dimension of the P homology. Working with HP defined over R, so it's a P homology space. Okay. The point here is that we established this, we spoke about this the last time, but each of the terms on the right hand side is a topological invariant. Recall that this was the quotient of the space of P chains to P boundaries, okay? And the dimension of the space of P chains depended on how we triangulated the space. But in taking the quotient, that worked out in the wash, and this was a topological invariant. So this didn't depend on how we did any of the triangulations. Yeah, it coded the global properties of the manifold. So every term in this alternating sum on the right hand side is topological invariant, and hence the Euler characteristic, the Euler character on the left hand side must also be a topological invariant. But as I said, this is probably not the definition that you grew up with. Okay? The definition that you've encountered in primary school is one that involves vertices, edges, and faces, ostensibly of a two-dimensional object like a cube. But it meant something like this. So recall that the typical definition it is that chi is the number of vertices minus the number of edges plus the number of faces. Certainly, this is true if you're talking about a graph, right? So this is the number of vertices, the number of edges, number of faces. Okay, and the point here is that this M here in this definition is some two-dimensional surface, and really what we're talking about is a triangulation of this two-dimensional surface. Okay. My statement is that when your teacher told you about this, they didn't give you the whole story. And actually a bunch of other things involved if I increase the dimension of M. Right? And that's involved in the triangulation of M into some superficial complex. So you have alternating sum, number of vertices. Vertices, remember, are zero subvectors. Edges are one subvectors. Faces are two subvectors. So if I go higher than dimension, I've got to add alternating sum more and more subvectors of higher degrees. Okay. The point is that I can write this thing in our more sophisticated notation as the sum equals not 2 of -1 is a p and dimension of CP. And then the point is, if I'm going to higher dimensions, I need to start at 2. I can, in fact, continue on to D. Okay. Is there a question?
Why is C not 8?
Good question. Why is it C not 8? I'll spend the rest of the lecture telling you why it's C not 8. Or rather, that is the same thing. Okay, so good. So, excellent. So, we made a definition here that the Euler character is the alternating sum of the dimension of HP of it. Okay. And I'm telling you that when you first encountered the idea of the Euler character as an invariant of some two-dimensional space, this was a truncated version of this statement, that it is the alternating sum of the dimension of the space of P chains. Okay, or rather, because we can express this in terms of basic syntheses, in terms of the dimension of the space of P syntheses. Okay. Here's the point. And I just made this claim just now. This is not so obvious that this is a topological invariant, right? Because what my simplices are, and certainly the dimension of the simplices, depends on how I triangulate the space. Remember, we could have a tetrahedral triangulation of the sphere, or we could have a cubic triangulation of the sphere. Right? Or we can have a soccer ball triangulation of the sphere. They contain a different number of vertices, edges, and faces. So the triangulation is different. So the dimension of CP of M is different. Right? Yet this is the same Euler character. So if it's a topological invariant here, it's a topological invariant here, which means that somewhere in this alternating sum, okay, all that localness that defines that comes in from the triangulation is getting washed out. So let me show you how that works. So the question here is, is this a topological okay. The answer is obviously yes, and to show you that the answer is yes, I have to show you that the sum is equal to this. Right. We're going to use the idea of exact sequences to demonstrate this. Okay, so for that I need to define the idea of an exact sequence. So suppose I have some set of vector spaces that is equivalent to some map between the vector spaces. So a set of vector spaces say VP equipped with equipped with maps FP, let's take VP to VP plus 1. Is called an exact sequence if the kernel of FP is equal to the image of FP plus 1. P minus 1. Okay. So, for example, if all cycles with boundaries, then the set of p chains with equipped with the boundary operator would constitute an exact sequence. Okay. It would be an exact sequence going in kind of the opposite direction, since this is about spaces and arrows between them. Okay. And in this case, the arrows go left to right if you want, and increasing order of p. If we're talking about chains and the boundary operator, the arrows go right to left. Doesn't matter, it's irrelevant in the discussion. Okay. The point is that if all cycles were boundaries, then the set of p chains equipped with the boundary operator map would constitute an exact sequence. However, when the homology is non-zero, that's when I have cycles that are not boundaries. Okay. In that case, the best we can hope for is that the kernel of the image of FP minus 1 is some subset of the kernel some subset. So the image of FP minus 1 is a subset of the kernel of FP. And the dimension of HP, measures just how close this equality, this comes to equality. Okay. So, as an example, it's all cycles boundaries and set CE with maps DP taking you from CP to the boundaries with the exact sequence. But if modeling is not vanishing, then image of P plus 1 subset of the kernel P, and the dimension of P is equal to dimension kernel P minus the dimension of image P minus 1 gives us a measure of how far short we're falling from how far short the set inclusion falls from equality. So now suppose I have some finite length exact sequence as follows. I'm coming from some generality to start off with, and then we'll specify the vector spaces are the space of chains and the maps are the boundary operators. So it will be clear from the general discussion how that will follow, and any gaps in the argument I will leave this exercise to be follow. So suppose we have the finite length exact sequence follows. Start with the 0 vector and F naught. Which takes me to V1. 1 takes me to V2. 3 2, etc. And this goes to F n - 1 to Vn, and then Fn takes me to 0. So a couple of points to note. Point 1 is this is just a vector space existing on the 0 vector. Two, I'm going to assume that F naught that the maps F are linear maps. So F naught in particular is linear, so it maps 0 to 0 and V1. So F naught is linear and maps 0, 0. Point 3 is that Fn, because it's an exact sequence, Fn maps Vn to 0, which means that Vn is the image of Fn-1. Finally, since the kernel of F1 is the image of F naught, it follows then that the image of F1 is contained in V2 is an isomorphic image of V1. It will help to have a picture of what's going on here. So let me choose n equals 5, and let's draw out these statements in a picture. The It's just to have some concrete picture of what's going on. So I start off from 0. And F naught maps me to 0. Let me just draw a picture and then we can talk about it. Zero, 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 zero. Okay. So we start off with 0. F naught maps us to B1. F1 maps us to B2. F2 maps us to B3. F3 maps us to B4. B5. To naught. 4. B5. The image F1, etc. Okay. All right. What we need out of this is a result from linear algebra called the range null space theorem. The range null space theorem tells us that the dimension of VP is the dimension of the image of FP plus the dimension of the kernel of FP. But we know that this is an exact sequence, so the kernel of FP is the image of FP minus 1. So this tells us that dimension of VP is the dimension of FP plus the dimension of the image of FP minus 1. Now we're ready to introduce the alternating sum that we want. Namely, the dimension of the image of F naught and the dimension of the image of Fn, given that it will map to 0, will vanish. Then the telescoping sum from, let's say, P equals naught to n of minus 1 to the P, and the dimension of VP. And this thing is just the dimension of V naught plus minus the dimension of V1 plus the dimension of V2 minus etc. All the way to the dimension of Vn plus minus 1 to the n dimension of Vn. Each of these guys I can write in terms of the dimension of these maps. So this is equal to, for example, the dimension of the image of F naught minus the dimension of the image of F1 minus the dimension of the image of F naught plus the dimension of the image F2 plus dimension image F1 on and on. So we get to plus or minus depending on n, dimension of the image of n plus or minus dependent on n, the dimension of the image of f n minus 1. Right. So this vanishes, that's 0. This is also 0. This is also 0. This guy is cancelled out. This guy with the minus sign. There's in here a term that will cancel out this guy because it will enter like minus sign. And then there's a term that will enter, if this is plus minus, there'll be a term that enters minus plus. We'll take out this one. So all of this the terms vanish either by cancelling each other out or the fact that the dimension is 0. And the point is that this telescoping sum of the alternating sum of dimensions of VP vanishes. In our case, the sequence of vector space that we're looking at is a set of chains equal to the boundary operator map, and the dimension of the kernel of dp. Okay, let's slow that down. For us, the VPs is identified with CE. So identified with CP, and And the map that we're talking about is dp that takes us from Cp to Cp minus 1. With the dimension of the kernel of dp equal to the dimension of the image of the p plus 1 plus the dimension of the p homology group. And this, together with the range null-space theorem, I'm going to leave this as an exercise, following exactly the same argument we just used. So that the sum from equals naught d of minus 1 to the minus 1 to the p dimension of Cp is equal to the sum equals naught d of minus 1 to p dimension of Hp. Which establishes the result then that the Euler character that you're familiar with from primary school as the number of vertices minus edges plus spaces is in fact the same as the Euler character that we defined here. And the oscillating sum of Betty numbers, the dimension of p homology group, and in fact the topological invariant. Okay. I can give you some exercises on this if you want a little later. But for the moment, I want to move on and show you I want to kind of clarify this link between homology and cohomology. In particular, I want to establish why we call cohomology cohomology. Okay, so when you learn about vector spaces and dual vector spaces, you have vectors and covectors, and that told you that the covectors we call today forms, forms were dual to vector spaces, and they were dual to vector spaces in the sense that I could define a well-defined inner product that took the product of covector space and vector space to the reals. Okay, so let me show you that the same is true in this case. So what we're going to do now is try to link up homology and cohomology. And as I said, this link is provided by the idea of an integral. So suppose I've got a m-dimensional manifold. And I'll take C to be some element of set of say R chains. Yeah. So this is some R chain here. And omega will be some R form on it. MR is some number between 1 and M. Then we can define an inner product as follows. We'll define the product that takes CR of M plus omega R of M to the reals by C inner product omega just being the integral of this R form over the R chain C. Okay. So you can see, and given that we define forms as things that you integrate and chains that as things that you integrate over, there's a natural pairing under the integral sign of forms and chains. And this natural pairing defines for us this inner product. So it takes a chain and a form and it outputs a real number. It can output complex numbers we're not talking about. Well, it outputs a real number. Okay. Clearly, this inner product is linear in both of its arguments. So it is linear in both of its arguments. Means that I can think of this as a linear map acting on C and vice versa. In the sense that if I take C1 plus C2 as two R chains and take their inner product with the R form omega, then this is the integral over C1 plus C2 of omega, which is the integral over C1 omega plus the integral over C2 of omega, the linearity of the integral. And similarly, if I take C and I find the integral find the inner product with omega 1 plus omega 2, where these are two forms, two R forms, then this is the integral over C of omega 1 plus omega 2, is the integral of C of omega 1 plus the integral of omega 2 over C, which is C omega 1 plus C omega 2. And the neat thing is, in this language of the inner product, Stokes' theorem was already a hell of a compact by our differential geometry standard, can be put into an even more compact form. Stokes' theorem then says that C inner product d omega, if this is a R chain and omega is an R minus 1 form, is equal to DC inner product omega. Right? You recall that Stokes' theorem told us that the integral of d omega, the integral of the derivative of an object over some region, is equal to that object evaluated on the boundary of that region. Okay. Only now, the hint that I'm getting from phrasing it like this is that the boundary operator and the exterior derivative are adjoint operators under the sigma product. Okay. So D
and D are adjoints of each other. Right. Remember, adjoint you define with respect to a particular inner product, and this is the inner product we're defining. Moreover, this inner product induces a natural inner product on the homology groups. So this guy induces an inner product lambda on elements of HR of M and HR as follows. So we'll define. So remember, HR consists of equivalence classes of K, and HR consists of equivalence classes of forms. So if I let C, equivalence class of C, be some element HR of M. So these are changing on our boundaries, and omega be in HR of M. Then find some inner product lambda, which takes HR of M plus HR M R by lambda of C omega find to be the inner product with C and omega, which is again that's the integral of omega of C.
Why is this a sensible inner product? Well, it's sensible because of the following. So suppose I take some cycle Z, some R cycle Z, and take two R forms, omega 1 and omega 2, that differ by an exact form. So omega 1 and 2 in omega R of M that satisfy that omega 2 is omega 1 plus d of some r minus 1 form, right? So the difference is just some exact form. And let's calculate then what this gives us. So if I calculate Z inner product omega 2, this is Z inner product omega 1 plus Z inner product this exact form by the linearity of our inner product. But this guy is just this is just dz inner product eta by this statement. And because this is a cycle,
the boundary of the cycle vanishes, and so this is 0. Which means that the Z inner product omega 2 is Z inner product omega 1. In words, what this tells us is that all elements of the cohomology class of omega give the same answer when you integrate it over a cycle. Similarly, if omega is some closed R form, and I take two R chains, C1 and C2, that differ by a boundary. So C2 is C1 plus D or something, let's say A. Then C2 inner product omega is C1 inner product omega plus dA inner product omega. Again, this guy vanishes because dA inner product omega is A inner product D omega, where D is a closed form, so D omega is 0. So C1 and C2 are the same. And the result false. So this is a well-defined inner product between HR and HR plus HR and the rings. So what this tells me, okay, so not just that, but what this means is that lambda of something in a product omega is a linear map on the equivalence class of C's, and similarly lambda with C in a product something is a linear map on the equivalence class of omegas. So this hints that in the same way vector spaces and covector spaces are dual, that these two vector spaces are dual. And I say hints that because it's not a given. And it's not a given because I have to first demonstrate that this is a map of maximal rank. In other words, that the dimensions of 8R and dimensions of 8 are the same. This is a non-trivial task. So I'm going to leave it here because I've run out of board. And I'll pick it up on Friday, in which I will just state the theorem under which conditions it holds, and it's called the Ram's theorem. And the Ram's theorem basically tells you that if F is a compact manifold, then the statement is true. That basically the Ram's theorem, in so many words, says that HR of M is equal to HR of M. Okay. Yeah.
What's happening on Wednesday?
Wednesday. We don't have a lecture on Wednesday?
Well, you said Friday.
Oh, yes. Okay, so we might have a lecture on. Yeah, just got to check. I think I thought that it wasn't at some point and might be double booked or something. But if I'm not, then we'll have a lecture on Wednesday. All right.